Welcome to section 8.2. This video is going to closely tie to the homework, as all of the questions that I've gotten, that I have prepared here, are from the 8.2 homework itself. And so 8.1 laid the foundation for you that you need here. But interestingly enough, as we go to 8.2 and 8.3, they don't do it all the traditional method. All the questions have you walk through the p-value method. And that's a great method. It takes a little bit of a detour from the traditional method, but the first initial stages are the exact same, the first initial steps. And so I think I can describe this to you very well. You won't need anything more than a calculator, any calculator that you've been using throughout the course, as well as your charts, right? And we'll model what it's supposed to look like. So let's take a look at this very first one. In a study of the accuracy of fast food drive-through orders, one restaurant had 38 orders that were not accurate among 328 orders observed. Use a 0.05 significance level to test the claim that the rate of inaccurate orders is equal to 10%. Okay. Does that accuracy rate appear to be acceptable? And so they'll have those follow-up questions like they do in the homework. But let's worry about the big test here and some of the wording that happens as a part of that. So let's go ahead and write our claim in symbols, because we know that that's our first step. Our claim is that the rate of inaccurate orders is equal to 10%. Okay, so that means our claim is P is equal to 0.10. We're making a claim about the proportion of all the orders that are at this restaurant, and we want to test the claim that they're equal to 10%. Our null hypothesis then is also the same thing. And so remember our goal. Our goal is to reject the null hypothesis. So the best thing that we can do is reject our claim. Okay, and so our alternative hypothesis is the claim if it can be, but it can't, because the alternative hypothesis has to be different from the null. And so this is a not equal to. So remember, for H1, the three symbols that could be in play are greater than, less than, or not equal to, nothing else. Okay, and so the the alternative hypothesis H1 has to be a statement that does not include an equality. And so whenever our claim is not in the alternative form, this is the one instance, our alternative hypothesis will be different. We do want to remember that not equal to implies two tails, where these two right here imply one tail. And you saw that in your 8.1 backup. That's going to be important for us to remember, that this is a two-tailed test. So I'm just going to write that right here. This is a two-tailed test. We'll need that in just a moment as we go to calculate the p-value. So let me erase this side work notation here, and we'll keep going. The next thing we need to do is find our test statistic. Well, we'll grab the only test statistic formula that has p's and q's in it. And it looks like this. Well, we know a lot of these things. We know p is 0.10. If p is 0.10, then q is 0.90. And they must have given us a sample size. Yeah, there are 328 orders. So what p hat is the sample percentage. So what came out of the sample? So what p hat is there were 38 inaccurate orders in the sample out of 328. So let's look at what that number is. In fact, yeah, let's take a look at it just for informational purposes. And then I'll give you my biggest suggestion. Whoops, I typed in something wrong. 38 divided by 328. This is 0.115854. So we're looking at a little bit more than 11.5%. Right, your decimal point's right there. So we're seeing the inaccurate orders being at 11%, and we want to test the claim that it was 10%. The best we can do is debunk that claim and say that it's not 10%. It's got to be closer to 11. But we'll see what we can do. So what I would suggest, instead of rounding that off at all and putting 0.116 or something like that, my suggestion is just let it all ride in your calculator. So what do I mean by that? Take the 38 and divide it by 328 and subtract away 0.10 and hit equals. You'll see a number there. Now you're going to divide by the square root of, use an open parenthesis if it's not there already, 0.1 times 0.9 divided by 328. You can close that parenthesis off if you want, and you get a z-value of 0.957073. Okay, or a z-value of 0.96. Awesome. Now we have our z-value of 0.96. That's our test statistic. So the way the p-value method works is we go and plot that. If you remember, what we're going to do for the p-value method is you plot it as its own z. So this is the z-score of 0, which is always right in the middle. And then we have this 0.96 that was our test statistic. And we're going to look for the area in the tail that's created. So how do we get that area that's in the tail created? Well, we go to our chart and we're going to look for the 0.9 row and the 0.06 column. Let's go look at that together. So let me go to Files here, and on my iPad, I'll go to all the charts because we'll eventually need the T-chart. But we got a 0.96 as our guy. So 0.96, travel on over, and we have 0.8315. Let me highlight that. So 0.96, 0.8315. See that there? I'll make it big. That's at the intersection of the 0.9 row and the 0.06 column. Awesome. So let's remember that, 0.8315. So we look up 0.96, and remember what 0.8315 is. Let me go ahead and put it in red. 0.8315. Doubting myself that I remember that right. Okay, I did. 0.8315 is the area to the left, but we want that tail area. That's going to help us get our p-value. So that tail area right here, and let me put that in green because that's what we desire. That tail area is 1 minus 0.8315. So let's see what that is. 1 minus 0.8315. That is 0.168. 0.1685. That's this area right here. Now technically that's not the p-value. And let me tell you why. So let me erase some of this stuff around it so that we can focus on that number. Remember this statement right here. We were two-tailed. It was a two-tailed test. So there is a separate tail down here because we didn't want to be right in the middle. We could be to either side. We didn't want to be the 0.10. We wanted to be to either side. And so whenever it's two-tailed, you double this tail area. So because of that two-tailed test, I'll come in here in blue. Because of it being a two-tailed test, we have to double that in order to identify our p-value. So when you go to type in the p-value, because it will ask for it separately, you're going to double 0.1685, and you're going to come up with 0.337. When you type 0.337 in for the p-value thing, it's going to say, good job, right? Excellent, great work. But that's our p-value. Now, that's not the end of our problem. The way the p-value method works is you find this p-value. Remember how we did that? We found the test statistic, we plotted it, and we found the tail area. Now, we would take the tail area if it was a one-tailed test, but it's two-tailed, so we got to double it. And we double it to get 0.337. And you'll watch us do other ones in just a moment. So 0.337, awesome. The next thing to do is to compare the p-value to the significance level. Okay. If the p-value is less than the significance level, that means you reject. that means you have strong data, because the probability that you're in that area is lower than the significance level. If the p-value is not or is greater than the significance level, then you fail to reject. So let's see what happens. What's our significance level in this problem? A 0.05 significance level. So the question is 0.337 less than 0.05? And the answer is no, it is not. What does that mean? That means we fail to reject the null hypothesis. It also means the data is not sufficient to, and the wording changes, but they'll give you some good wording in there, to know that the percentage is not 10%. So we have no basis to say that it's not 10%. That's what we were hoping to do. I know it was our claim, but since our claim was written as an equality, the best thing that we can do is reject it. So the 11.6% is not far enough away from the 10% for us to disprove that it's 10%. In fact, it's that's p-value is super high, right? It has a 33% chance of falling in there. And so that's not far, or that's not a significant thing. We need to be less than 5%. So we fail to reject, and the data is not sufficient to know that the percentage is not 10%. So we get to review that again. Here's a second problem, right? And we can talk about these things another time. So let me switch to another color. Suppose 108 subjects were tested with a drug that's used to treat pain. Wonder if that's supposed to read something different. But we'll run with this. So I'm going to change that to suppose, and again I got this from the online homework. I read it to this. I used a screen dictation in order to do this. But suppose 108 subjects are tested with a drug that's used to treat pain, and 52 of them develop nausea. Use a 0.05 significance level to test the claim that more than 20% of users develop nausea. Okay, let's see what the strength of data is here. And so, okay, so we want to test our claim. Well, what's our claim? Our claim is that more than 20% develop nausea. Well, 20% is a percent, and I'm claiming that percent is above 0.20. Our null hypothesis is always an equality statement between those symbols and the number. And the alternative hypothesis is the claim, provided the claim's not equal to. And the claim's not equal to. Now, this is not and not equal to, so this is a one-tailed test. That's why they stress that in 8.1. So it's a one-tailed test anytime it's a strict inequality like less than or greater than. The only time it's a two-tailed is what we saw before, a not equal to. And those are the only three symbols the alternative hypothesis could even have. Okay, so this is a one-tailed test. Let's keep that in the back of our mind. We know what we do need to do next. We need to go get the z-score by taking p hat minus p divided by the square root of pq divided by n. What's p hat? Well, let's skip that for a moment. What's p? P is 0.20. Where does that say it? Like, how are you getting that, Jensen? Right here. Statement of the null hypothesis. It literally says p equals 0.20. That's what you're assuming. Remember what you're finding. You're finding out how far the sample value is away from the benchmark of 0.20 in this case. This is 0.20, 0.80, right? 1 minus p divided by n. N was 108. What we don't have is p hat. Well, we know what p-hat is. It's the percentage of subjects that experience nausea, and 52 out of 108 experience nausea according to the numbers that I had typed in. And that's over 48%, right? It's 0.4814, and it just keeps going. So what does that mean? It means I would plug it in like this. I would just leave it. It's less writing. 52 divided by 108 minus 0.2 equals, divide by the square root, don't forget your open parenthesis, of 0.2 times 0.8 divided by 108. And we get a z-score of 7.31. And it keeps going, but it rounds to 7.31. Well, that makes a lot of sense. We just found out that 48% is super far above 20%. We not have known that. It really depends upon the strength of the data. For example, if those numbers came from only 5 people, we'd have a significantly lower z-value. But we have a high one. So we're going to plot that guy. Right? The p-value method is to plot that z of 7.31. When you look up 7.31, you're not going to be surprised that it's in the 3.5 and higher category. And so we know that down here is 0.9999. So this is 0.0001. So what's the p-value? The p-value is 0.0001. Why does it stay that way? Because it's that times the number of tails. And the number of tails is 1, so it's just 0.0001. Now the question is 0.0001 less than the confidence the stated level of significance of 0.05? And the answer is yes. Because the answer is yes, you're going to reject the null hypothesis. Anytime you reject the null hypothesis, you're making a very strong statement. You're saying, okay, I know it's not 20. So it's got to be above 20 because it's got to be on the same side that the data is coming out at. So then you're right, there is sufficient evidence. And each of the 10 homework problems are going to get you to practice with this. There is sufficient evidence to support the claim that the percentage of those taking the drug and experiencing nausea is more than 20%. So they're going to have some drop down menus and stuff for you to choose the right wording. Get that wording down. That wording is important because we want you to recognize that when you reject, you've done something strong. You are saying, oh my goodness, that data is so strong. That 48% is so far above the 20% that there's no way that if we talk to more than 108 people, it would ever drop to 20, which means it's above 20. Right? What's happening here is we're finding, oh my goodness, the 11.6% is super close to the 10%. So close that I can't really say that if I talk to more than 328 people, that it might not creep back down to be 10. This one might creep down, but there's no way it's dropping to the 20 level. It has this 48% benchmark or anchor, for lack of a better way to say that. And yes, it might fall below that, right? Because there's error in that, but it's not going to fall so far below that it comes to touch that 20%. Let's take a look at this last one. Also gotten from the homework. In a study of 810 randomly selected medical malpractice lawsuits, it was found that 481 of them were later dropped or dismissed. Use a 0.01 significance level to test the claim that most medical malpractice lawsuits are dropped or dismissed. So if somebody doesn't do the homework, they may not be able to know what to do with this problem when they see it on the exam. When you read the claim, The claim doesn't use any numbers. It just says most. How are we going to write most? Well, we got to think about what most means. So if we have most of the senators voting for a reform package, then we have more than half of them. If we have more than half, then we have more than 50% of them. And that is the way we deal with most or a majority. It is a claim about the percentage, not a raw number. If most people are doing it, more than 50% are doing it. That's our claim. Our null hypothesis is always equal to, and our alternative will always be the claim if it can be, and it can be this time. Now, why can it be? Because the claim has a strict inequality. The claim does not have an equal to sign in it. Okay, and so that's what we have for our alternative hypothesis, which means that this is, again, a one-tailed test. Remember, the only time it was two-tailed is when the alternative hypothesis had a not equal to sign in it. Okay, and so keep that in mind for future. Oh, no problem. We know what to do. Z is equal to p hat minus p all over the square root of pq over n. Again, most of these numbers are here, 0.50. If p is 0.50, then q is also 0.50, and n is 810. Now, we need to know what p hat is. P hat is 481 over 810. Let's see what that number is. 481 divided by 810. Oops. Okay, kind of goes on for a while. So it's about 59%, 0.593827. So what we're trying to find out is this question. Is 59% so far away from 50% with our data that we're sure that if we talked to more people and got the true percentage of everybody, that it wouldn't drop down below 50 or to the 50 level? Let's see. So again, when it goes on forever or goes on for a while, I recommend doing that because it's just as easy. 481 divided by 810 minus 0.5 equals, divide by the square root of 0.5 times 0.5 divided by 810. Oops, I forgot my parentheses, so I'm going to have to go back and put in a parenthesis. So give me a second. Okay, I would have had the wrong answer. Okay, I get a z value that's also very high, 5.34. Okay, so again, I got these from the homework. So even though it was only a 9% difference, that was significantly high. And so we look at that, and it's 5.34. So we know the p-value method now. We have a z-score of 0 in the middle, and we're plotting 5.34. We look up 5.34. And we get 0.9999. We don't even have to look because we know it's in the 3.5 or higher category, which means this is 0.0001. So the p-value is equal to 0.0001 times 1 because it's a one-tailed test. Now again, how did I know it was one-tailed? Because anytime it's a greater than or a less than in the alternative hypothesis, it is a one-directional thing. It is a one-tailed test. And so we get 0.001. 0.0001 is less than the stated level of confidence of or significance of 0.01. So I'll put is 0.0001 less than 0.01? And the answer is yes. So therefore, what are we doing? We're going to reject the null hypothesis. And there is sufficient evidence to support the claim that a majority of lawsuits are dropped. Okay. Okay, so there is sufficient evidence to support that claim. So remember, these last two were one-tailed tests. So let's see what made this other one different. What made this one different is when you went to write the alternative, it was a not equal to. Anytime it's a not equal to, it's a two-tailed test. And you have to double that p-value or double that lookup value to get the correct p-value. And then you're going to compare that p-value. This was also the only one where the p-value was not less than that. And anytime that happens, you're going to fail to reject, and the data is not sufficient to know that the percentages is not 10, right? And they'll have nice drop-down menus. So this should mirror the homework pretty exactly. And so take a look at these p-value examples before going and looking at that. I guess you already have, or you wouldn't have been this far in the whole video process. So, all right, have fun with it and let me know what questions you have.